Hello everyone, welcome to a short series of videos. These videos are designed just to help you out a little bit with chapter 1, which you can use for the holiday homework. So just to make your life a little bit easier, just go through a few key ideas that you might have missed. So first up, we have functions. So the chapter is all about functions and relations. So before we start that, we need to be pretty comfortable with the idea of a function. So it says here, a function is defined as a set of ordered pairs. They're basically two sets. There's the domain and the range. So the set of the domain, we put in our inputs. That's what domain is. The inputs are the x values, and we get our outputs, which are part of the range of the values that we could get out. Now, the defining feature of a function is that for every input, we're going to get out a unique output. So let's have a look over here what I might mean. So we have an x value, which is also known as an object. We put it into a machine, which is called the function. We say f of x, so the function with an input of x, and we get out a value of y. So we can see if I put in a into this function, I'm going to get out d. If I put in b, I'm going to get out e, etc. Input, output. Make sense? Okay, now a couple of things that you need to be around is that if I put in a function, if I put an input into the function, I could possibly get I could possibly have two inputs that give us the same output. This is completely fine. So for example, maybe A goes into the function, gives us D, and maybe B goes into the function and it also gives us D. So both B and A give us D. Here's an example over here. So let's say we have the function f of x is equal to x squared, and I put in an input of -2. If I put -2 into this function, we just replace the function. So instead of writing x, I put -2, substitution. We get 2 times 2, that's 4, and a negative times a negative makes a positive, so we get 4. And if I put in 2 into the same function, I get 2 squared. I get in 2 squared, which is also equal to 4. Okay, so we can see that there were two different inputs that gave me the same output. This is still a function because it's not like I put in -2 and I got 4 and something else. I got out a unique output. That's what I mean. I got out a unique output. Here's an example of something that is not a function. If I have the relation or the equation g of x is equal to plus or minus the square root of x. This is where we start encountering some problems because let's say, for example, I put in, let's say, 9. I'm going to get plus or minus the square root of 9. Now, the square root of 9 is equal to 3 because 3 times 3 is equal to 9. So therefore, this is going to be equal to plus 3 and minus 3. Now, the problem is we don't get a unique output here. I put in an input and I got out two outputs. This is not a function. So a function needs to give me a unique output. This is not unique. So there we go. So here's a little way of identifying whether or not something is a function. So let's have a look at this real quick. Just change the color up here. So let's suppose we look at these graphs here. So this graph over here is called a one-to-one type function because if I put in an input, let's say I put in this x value here, let's call that x1, I'm going to get out a unique y value, this one right here. So let's call that one y1. I put an x1, I get out y1. It's not like I put an x1 and I get out y1, y2, and y3. There is a unique answer. This is what's called a one-to-one type function. Because for every input, I get one output. Here's one a bit like what we were looking at before. If I put in a value into this equation, like let's say we had here, we put in -2, I got 4, I put in 2, I also got out 4. Same thing happens here. So if I put in this value here, let's call that one x1, let's say this one over here is x2, I will get out the exact same value if I drew that properly. So we can see here, they are both the same value of y that comes out the front here, which is why we call this a many-to-one type function. There are many inputs that give us the same outputs. This is a function. The way that we can check if something is a function is by using something known as the vertical line test. Basically what this means is we just draw vertical lines. And we see, why is that not erasing? What's happening here? There we go. We put in vertical lines. We can see that for both these graphs here, those vertical lines are going to pass through the graph once. So we can see it passes through here. There is only one output. Have a look over here. If I try and draw a vertical line through this graph, this is like a square root sort of graph. It's just freezing on me. Wonder why that's happening. There we go. If you imagine that they're vertical lines, so straight lines like that, we can see that they pass through the graph twice. Like this one passes through here and here. So that makes this a one-to-many type relationship, because if I put in one value, like let's say I put in this one x value, I'm going to get out two possible y values. This makes this not a function. We call that a relationship. So that's not a function. It failed the vertical line test. Same with this one over here. We try and draw some vertical lines. It passes through twice. So therefore, this is not a function, this is a relation. This one also fails the horizontal line test as well. So horizontal line test, it is important. It helps us determine whether or not something has an inverse. So inverse is basically where we swap the y and the x-axis around. So we would say that this one here, the one-to-one function, has an inverse, or it's invertible, I guess we would say. And then everything else here is not invertible. Simply because, well, this one's not invertible. This one is invertible, weirdly enough, because if we were to swap the x and the y-axis, we would, in fact, get a parabola, which, as you can see here, is a function. So this one, its inverse would be a function. It is not a function. And this one is not a function, and it's also not invertible. So its inverse is not a function. So, yeah, like I said here, to verify if a graph represents a function, apply the vertical line test. If a vertical line intersects the graph more than once, the graph represents a relation and not a function. Okay, so now this is important here. Mapping notation. So this is the way that we write functions. We say f of the function. So we say f of the function, which is basically the name of the function. Okay, so f of the function is defined by the domain going to the codomain of f of x is equal to ... We're going to write in the rule of the equation there. So in this notation, D is the domain, R is the codomain. It is always R. So just don't worry about this too much. I'll talk about it in a minute, but the number after this little arrow here is always going to be R. Basically, the codomain is the set of all possible outputs. The domain is the set of the inputs that we're going to be allowing. So let's have a look at this over here. We've got a graph over here. So this graph here, this defines the equation y equals x squared. Just double check that it does. If I put in x equals 3 into this equation, I get out, let's see. So if I put in y equals 3 squared, I'm going to get out 9. And if I put in y equals -2 squared, I'm going to get out 4. So in both cases, that gives us the output that we can see on the graph. So that seems to check out. Now notice the use of the open circle and the closed circle. So the open circle means inclusive. So this is inclusive. And the closed circle means exclusive. What that means is this value here, we're going to accept values right up until this point. So maybe, for example, -1.999999999. That's going to be defined. But -2, that's not defined. So the function is only defined right up until -2. And over here, the function is defined up to 3. So it's defined for 2.99. That's fine. It's defined for 3. That's fine. It is not defined for 3.0001. Okay. So the way that we write this down is, and there is actually a small error here, this should be a closed bracket. So open bracket is used to define, so notice it's like a round bracket. There's no curve on that. Open bracket is used for inclusive points. Sorry, I've written this the wrong way around. That should say exclusive. This should say inclusive. So inclusive, exclusive, yeah. So we are excluding this point, so we use a round bracket, and we're including this point, so we use a square bracket. So this can be written in the form f, so the name of the function, we can call this whatever we like. We can call this Steve, we can call this G, it doesn't really matter. It does not have to be f is the point. G ... so colon, -2 to 3, square bracket, round bracket. That is important. By the way, it's really important that we have these numbers listed the right way around. For example, we would not write 3 to negative 2. This is wrong. So we always have to list the smaller number first. That's the point I'm trying to make here. So even if the brackets are correct, we have to list the smaller number first. So we have that, 2r, always r, and then we have the comma, f of x equals x squared. So that's just the rule of the equation. So let's have a look at a few key details here. So first up, we have the concepts of the codomain. So I told you not to worry about it. It's always going to be r, but for argument's sake, if you are interested, there are things called complex numbers. So basically, let's suppose we have a function. Let's say we have a function square root of x. Now, square root of x, normally this number here needs to be a positive number. Why does it need to be a positive number? Well, let's have a think about it. So let's say we have the square root of 9. The square root of 9 is equal to 3 because 3 times 3 is equal to 9. That's the definition. Notice that also negative 3 squared is also equal to 9 because negative 3 times negative 3, negative times negative, makes a positive. So we could almost say that there are two answers here, 3 and negative 3. We don't though. The square root, it's always just going to be the principal answer, so the positive answer. By contrast, we would say that the solutions to this equation are x equals, so let's say that is 9 is equal to x squared. This will have the solutions negative 3 and positive 3. It has two solutions. This only has one solution. So this is a function. Therefore, there is a unique output. The square root is a function. Okay, we don't write it as plus or minus square root. Okay. Anyway, so getting back to this, let us now consider the square root of a negative number. So if we have the square root of a negative 9, what will that be equal to? Well, it's not 3, because 3 times 3 is 9, and it's not negative 3, because negative 3 times negative 3 is equal to 9 as well. So this is undefined, but it's undefined over the real numbers, which is to say there is no number that lies on a number line. There's no number that lies on a number line. Doesn't matter where we look. There's no number that is going to satisfy that relationship. But there are numbers that don't lie on the number line that satisfy this relationship, and they're called complex numbers. You don't need to worry about them here, but if you were to take specialist maths, you might see equations written like this. You might see them written like, let's say, f of all of the real numbers. So we're going to accept real inputs, and we're also going to accept complex outputs. So it might say this, in which case we're saying that we're allowing complex solutions to this equation. We would need two-dimensional axes to depict these solutions. You don't need to worry about that. The point that I'm trying to make here is, firstly, if you're confused about all this, for argument's sake, for the purpose of methods, you will only ever see the codomain written as R. But basically, it's just, if you want a quick answer, it is just the list of numbers that are possible to accept as outputs. Again, you don't need to worry about this. It's just always R. Move on. Okay, so implied or maximal domain, this is something that you need to be aware of. This is the domain over which the function could possibly be defined, i.e. the set of all possible x values. So a real quick explanation to show you this. Consider the function f of x equals 1 over x. Let's consider a few outputs. So let's say we have f of x. Let's say we put in the inputs x equals negative 1. What's that output going to be? Well, that's going to be negative 1. That's going to be 1 over negative 1, which is negative 1. Okay, that works. Let's now consider x is equal to 1,000. Then we're going to get f of 1,000. That's going to come out as 1 over 1,000. That's a pretty small number. Now let's consider something else. Let's say we have x is equal to 0.00001. And we put that into the equation, we get f of 0.000001, however many zeros it is, I don't even know if that's right. That's equal to 1 over that very small number, and that is equal to a big number. If we put 1 over a small number, we get out a big number. Okay, point I'm trying to make here is I can put in any value that I like into this function as an input, and I'm going to get out an output, except in the case if I put in 0, because if I put in 0 into this equation, I'm going to get 1 divided by 0, which is not defined. So therefore, for this function, the implied domain is all of the real numbers, excluding. Notice we always write this excluding symbol with a slash going in this direction. Don't get that wrong. And then we use curly brackets for the values that we are excluding. So this is set notation. So all of the real numbers excluding the element of 0, because the function is undefined when x is equal to 0. Okay? All right, so let's practice this idea. So we've shown part of the parabola y equals x squared just over here. First question, explain why this is a function. Okay, so again, the way that we check to see if something is a function, we apply the vertical line test. So I'm going to draw a bunch of straight vertical lines here. They're not very straight. That's fine. We can see here that each of those lines passes through that graph once and once alone. So we can conclude, based off of this, that the function passes the vertical line test. And therefore, it is a function. All right, now it says state the correspondence. So the correspondence of this graph is a many to one correspondence, because we can put in many possible inputs and we're going to get out the same output. So what I mean by that is if we look over here, if I put in 2 into the equation x squared, I could put in 2. So maybe we put in 2, we get out 2 squared. And also if I put in -2, I get out -2 squared, which is equal to 4. So they're both equal to 4. So there are many possible inputs that give us the same output. So this is a many to one type of correspondence. So that's what we looked for. Now we need to express the parabola in function notation. So what we need for this is we're going to write it as, okay, we're going to name this function f. I could call it anything I like. I could call it g. Doesn't matter. Then I'm going to list the domain. So let's have a quick look at this graph over here. So we can see here that we're going to include the point. So let's get this right this time. So we have include the solid point, and we're going to exclude the open points. So we're including this point, excluding that point. Therefore, we're going to use square brackets for the point that we're including. So remember, this is the x values we're looking at, the inputs, up to the value 2, which is the x coordinate of this ordered pair here. So that's the x value. That was the x value up there. So that's our domain. We're going to say that domain, and we're going to accept just real output values. So our codomain is r, and then we're going to write f of x is equal to x squared. So that's the rule for the function. So domain, codomain, f of x equals r. Cool. Last question. This question says, what is the image of the function when x is equal to -2 times √3? Now, in case you forgot, objects, this is known as the input, or the x value, they all mean the same thing. An image, this means the y value or the output. They also all mean the same thing. So what this question is basically asking us is, what is the output when we put in an input of -2 √3 into this equation? Now, firstly, maybe we just need to double check. Are we going to accept -2 √3 here? Let's have a think about it. So √3 is less than √4. It's less than √4. So hard to write with this thing. And it's larger than √1. Now, square root of 1 is equal to 1. Square root of 4 is equal to 2. So therefore, √3 is somewhere between 1 and 2. And over here we have -2 times √3. So therefore, -2 times √3 is going to be, well, let's have a think about this. So -2 times 2, because what I'm doing here is I'm timesing all of this by -2. And I want to see what the relationship between these values is. So -2 times 2, I won't put in my symbol here yet, that's going to be equal to -4. And -2 times 1 that's going to be equal to -2. Now, if you see here, if we multiply by a negative, that's going to reverse the direction of these inequality signs. So that's actually going to now face in this direction. And if we just look at this, we can kind of see that that makes sense because -2 is in fact larger than -4. It's closer to 0. It's a more positive number. So therefore, we can conclude that -2 root 3 is in fact greater than -4 and less than -2. So therefore, it is going to lie within our domain. So the point being, the function is defined. The function is defined. So now we need to figure out what the value of the function is. That's just to double check here that we are in fact going to get a unique output. So, all right, let's put this value into the equation. So we know the value of the function is f of x is equal to x squared. We're going to put in an input of -2 root 3 into this function. So that means I'm just going to replace the x with that there. So let's say this is our x value. So x, this is the x value, -2 root 3. So I'm going to put that in, -2 root 3. I'm going to leave the function written as it was before. So that means we're going to write it as that squared, and therefore the output is going to be, well, -2 squared times root 3 squared. That's how we could write this. We can distribute the square. That is one of our index laws. -2 squared, that's equal to 4. And then we have root 3 squared. When we have a square of a square root, those two things cancel each other out. We're left with 4 times 3, and that is equal to 12. And that's the answer. So we would find that the ordered pair, -2 root 3, 12, lies somewhere on this graph. It's going to be somewhere up here. Somewhere around here, I guess. Oh, -2 root 3 of 12. Somewhere up there. Doesn't really matter. The point being is that it lies within this domain, so it will be defined, and that's the value of the image, which is the same as the output. All right, that's the first video. I'll catch you guys in the next one. See you soon.